is lesson 5 for the gas law unit in Chemistry 1. So in this video, we are going to first talk about standard temperature and pressure, and this is really a review because we mentioned this before. But because gases vary by volume in different locations due to temperature and pressure differences, scientists have come up with a way to standardize volumes, temperatures, and pressures by having a reference point or a frame of reference for gases. And this is so they can share data and have the same corrections done to their gases. So this is defined as 1.00 atmospheres and 273 Kelvin, which we know is 0 degrees Celsius. So the gas law that we're going to look at today is called the ideal gas law. Ideal because this is the epitome of what gases should do, but they actually don't behave this well, but this is what they should behave like. And this is a combination of 3 gas laws, 2 of which that we have done, which is Boyle's and Charles' law. We did not mention Avogadro's law, but it deals with volume and moles. So that one's very similar to Charles' law. It's the same setup, but instead of temperature, we have moles. So the more moles of a gas, the bigger the volume, which is pretty obvious. So we're really not going to go through the derivation much, other than this is the equation right here. And it's a combination of Boyle's, which means that pressure and volume is some kind of constant. Charles, V1 over T1, is another constant. And Avogadro's, which is V1 over N1, is another constant. So when all of these are combined together, we get P1 V1 over T1 N1 is equal to a constant. This constant R is our 3 constants here put together, and it's called the universal gas constant. And then they rearrange this to get rid of the fraction, and we get this equation right here. So just like we did for the combined gas law, where we took the equations and put them together, we do the same thing here. So what we have is this equation, PV equals nRT, where P is going to stand for our pressure. And in this case, it has to be in atmospheres. So if it's not in atmospheres, we have to turn it into atmospheres. N stands for the number of moles. T is temperature. And that must be in Kelvin. V is volume, and it has to be in liters. And R is the universal gas constant. And it has a lot of different values. Put the gas in there, universal gas constant. But because of the version that we're going to use, it has some weird units that will cross out everything, give us what we need when we put it into the equation. So this value that we're going to use is 0.0821 liter atmospheres over moles Kelvin. So the units here tell us what the units have to be in all of these. So let's look at an example. How many moles of oxygen gas are in 5.6 liters at STP? So with this, STP, standard temperature and pressure, we know is 1.00 atmospheres and 273 Kelvin. So that's the definition of STP. So like we've done with all of our other gas laws, we're going to define our variables. All but one of these is going to be known. R is always known. Since it's a constant, we can put in that value. So our pressure, we said, was 1.00 atmospheres. We're given a volume here of 5.60 liters. Our question is, how many moles, so that's our question mark. And since we're at STP, our temperature is 273 Kelvin. So all we have to do is put these into PV equals nRT. So P is 1 atmosphere. Volume is 5.60 liters. N is our unknown, so I'm going to leave it in as N. Our R value, and then our temperature. So we need to get N by itself, so we're going to divide both sides by our universal gas constant times our temperature. So that crosses out that and leaves N by itself. So we take 1.00 times 5.60, hit equals, divide by 0.0821, hit equals, and then divide by 273. And we round to 3 significant figures, and we get 0.250 moles for our answer. So that is our first problem. There is a second problem on the next page on the back of this, and that is right here. So we are given moles, volume, pressure, and we want to know what temperature is. So we are given 4 of our 5 variables because we know one of them is a constant. We're never ever going to solve for R. It's always given to you. So 0.0156 is our moles. Volume, 7.46 liters. Our pressure is in atmospheres. And our temperature is our unknown. So now we are solving for T. So PV equals nRT. So pressure, 0.985 atmospheres, times our volume, 7.46 liters, is equal to N, which is moles, times our R value, times temperature. So in this case, we are solving for T. So again, to get T by itself, I'm going to divide by our number of moles and our R value. So what I do to one side, I have to do to the other side. Crosses out our moles and our R value. We get T by itself. And over here, we put in 0.985 times 7.46, hit equals, and then divide by the 2 numbers in the bottom. And we get a pretty high temperature, 5,740 Kelvin for our temperature.